My name is Peter Willing and thank you for joining us. Today's session is covering lithium-ion battery recycling, a topic that's always brought up in any discussion, whether it be from a technical stamp or whether it be someone saying, well, what happens in 20 years if I've still got my car with the battery? So there's a whole sort of raft of information that I'm sure we're going to glean from you two guys. So today we're delighted to have Sam Haig and Anwar Sattar, who are going to talk us through recycling. So without further ado from my side, I'll hand over to you guys. Thank you.
Thanks, Peter.
Thanks, Peter. Sam, I'll let you introduce yourself first.
Yep. Good morning, everyone. My name's Sam Haig. I work for a company called RS Bruce. We're based in Sheffield, and our core business is in precious metal recycling, but we are establishing also a lithium-ion battery recycling facility. Before I was at RS Bruce, there was a company called Axion, which is a subsidiary of S. Norton metal recyclers, with big vehicle recycler, and that's where Anwar and I worked together for a few years. So it's nice to be back talking again, Anwar.
It is indeed. So I'm Anwar Sattar. I work at WMG. I lead the battery recycling activities for Warwick Manufacturing Group, which is part of the University of Warwick. At WMG, our core aim is basically to help industry and keep the industry in the UK at the forefront of technology. Of course, I'm eternally grateful to Sam because after finishing my PhD, he is the first person to, well, I was offered two jobs. One was by the University of Manchester and one was by Sam. The University of Manchester one was looking at recycling of waste bedpans from hospitals, and Sam's was battery recycling. So
I didn't know that.
It was. And actually, you know, if I'd taken that job, I'd probably be on, you know, Hospital Waste Live or something, talking about bedpan recycling. So obviously, you know, I'm grateful in that respect. Sam gave me my first job at Axion, and we worked on battery recycling, and then, you know, so I think it'd be a good place to start the discussion around, you know, sort of looking back at the history of battery recycling, or in particular lithium-ion battery recycling in the UK. So, for example, as far as I know, the first thing that anyone did in the UK was a company called AEA Technologies, which
2004, wasn't that around about then?
Yeah, so it was early 2000s. They came up with a process. Do you remember what it was, Sam? Or
I don't remember what it was exactly, but it was something to do with distilling the electrolyte and.
Yeah, so their aim was to recycle 100% of the battery, and although, you know, that's it's an enviable task, the issue is
challenging one.
Yeah, it's a challenging one, and obviously there's an interplay between economics and throughput. So if you want to explain a bit about that.
Yeah, well, I mean, it's a challenge in any kind of processing sector at all, but I think especially so in recycling, because one of the big sort of challenges in recycling is that, unlike most other manufacturing processes where you start with pure materials and you put them together to make a complex product, in recycling you start with a complex material and you're trying to break it down to make lots and lots of pure materials, and there's always a trade-off between purity and recovery and throughput, and you can sort of have two or maybe even just one of those three, but you certainly can't really have all three. So yeah, if you're trying to, you know, get a plant where you can run things through really quickly, you're going to have to balance your purity and your recovery rates against that. Whereas if you're really aiming for high purity and high recovery, then you're going to have to be very methodical about how you do things, and obviously that leads to additional time and additional cost. Yeah, absolutely.
Yeah. So if we look at lithium-ion batteries, there's about 4 materials within lithium-ion batteries. You've got your nickel, you've got your lithium, your cobalt, and your copper. And together these account for about 90% of the value within the battery. So if you start off with a process where you want to recover the electrolyte, you want to recover the plastics, you want to recover the graphite, etc., you know, what you're doing is you're putting an enormous amount of energy into it, and all you're doing is you're just getting an extra 10%. And that's if you can, you know, if you can recover them at a purity where you can sell them, which again,
and that's another sort of real challenge that's sort of ubiquitous across the recycling sector, which is at what point have you done enough? and at what point does it start costing you more money to get materials out than you're actually getting the value. So you might be getting something that's got a value of £100 a ton or something, but if you're expending £200 a ton to get that, then what's the point? And equally, it's the environmental thing. What's the environmental benefit of recovering a certain material if you're expending more energy and etc. to get that out when there might be a better route for it, and making
So the initial, I guess, the initial work done by AEA Technology, they didn't really look into that aspect. They just wanted to recover as much as they could. And so that's one of the reasons why they probably didn't make it. But the other reason was a lack of feed. So, in 2004, lithium-ion batteries were still a relatively young technology. And, there wasn't enough material to sustain a process. And then I guess the other thing was, although they had the initial funding, they did their research, but then you need more funding in order to make a pilot plant and then run it for a couple of years so you can iron out the processing issues. So since then, of course, we've had a number of other projects. So one of them is Amplify, which explained.
Well, I think sort of 2004, what happened with AEA, and then there was quite a long sort of lack of anything happening, and obviously the other battery, the wider battery recycling sector has grown up, and you've got you've got your lead acid, and you've got some alkaline going on, and you've got the incumbent sorters. And the people who do the sorting into different chemistries. But I think, what's been really good about this whole sort of the push in the last sort of decade or so on going to electric vehicles is that people have started thinking about, well, it's not just a case of making them, you've got to deal with them afterwards. So, a lot of these funded projects, even if it hasn't been the main aim, there's always been a thought of this battery pack or this advancement that we're developing. How does that affect end of life? And that was something that was really important in the Amplify project, which was kind of really, as far as I remember it, kind of the flagship #1 sort of big investment project in lithium-ion batteries back in 2000 and I'm trying to remember now.
2016.
Something like that, 15, 16, yes. And that was really a big consortium, big project looking at designing a new type of battery pack that could be modular and flexible. And there was a whole host of people involved. There was WMG and Jaguar and Delta and Potenza and various other people. But what was really good was that we were looking at end of life as well. So we were looking at, well, we build this battery pack. What can we do with it when it reaches end of life? And that was kind of knitted into the design as well. Yeah, and that kind of kicked off all these other projects like the Relib and the Recovas and everything else that's happening nowadays.
Yeah, so I remember going into the meetings in the Amplify project, and the sort of the design guys were like, "Oh, we're going to use glue, we're going to weld these together, blah blah blah," and we were like, "No, it's totally unrecyclable." And even though we were a really small partner, we actually had quite a big input, and a lot of the stuff that we mentioned in those meetings, the next generation packs that will be coming on in about 3 or 4 years time, they'll have incorporated a lot of the learnings that came out of that project.
Yeah.
So it takes about 10 years from sort of concept all the way through to commercialization, and that's quite a long, sort of lead time. So yeah, that's a bit of a challenge, because in the meantime, there's tens of thousands of packs that have come into the market.
Yeah, it can sometimes feel a bit difficult, because you sort of, as you say, you say stuff in a meeting, and maybe it doesn't quite get the impact that you think it's going to get, but actually you planted a seed. And then when it comes to sort of the next discussion, actually, it's the next design that has that feature that you wanted improved. But again, as you say, you don't see the benefit of that in the recycling sector for 10 years or 15 years. So, it's. But I agree that it was really nice to see all the designers really considering what we were thinking about, and it's just another design constraint, because they already have to deal with environmental cost, safety, performance, weight. You're just adding one more constraint, and that's their job. Their skill set is to deal with all those constraints and come with a design.
Yeah, and designers can do it. I mean, engineers can come to a lot of solutions. They just need to know what the problem is. You know, they need somebody to tell them what the problem is. Once they know what the problem is, then they can always design for it.
Yeah, that's
okay. And I guess then moving on to now. So one of the flagship projects at the moment that's been funded is the Recovers project, which we at WMG had quite a bit of an input into writing. The Recover stands for Recycling of EV Cells from Obsolete Vehicles at Scale. And basically, its job is to establish the end-of-life recycling infrastructure for electric vehicles and batteries. So coming to that, I guess now, Sam, your company, RS Bruce, is the only company in the UK at the moment that's actually shredding lithium-ion batteries. So there's a lot of companies that are claiming to do it, but nobody's actually doing it. Whereas you guys are the only ones that are, physically, you've got a process going. So let's talk a little bit about the challenges that you faced. So obviously there's three, I guess there's three stages to this battery recycling. There's the pre-shredding, so once you receive the packs. Then there's the the sort of the processing itself, so the shredding of it, and then finally there's the post-processing. So what do you do with the material once it's shredded? So if we start with the pre-shredding, or
Well, I guess even even before that, there's not just the technical side, but there's also kind of the economic decision, and that's the thing that AEA maybe fell down on partly, which is are you going too soon, or are you going to miss the boat? So that's kind of a big question, and it's a decision that we made that we didn't mind if we went a little bit too soon. We'd rather go too soon than miss the boat. But yes, I mean, you're right. So discharging and dismantling, that's kind of the first challenge. And again, it's all about trade-offs, and it's all about understanding what you're up against. So I think one of the big things in dismantling and discharging is the time and the work that goes into it. And it's skilled work. It's work that needs training. It's work that needs understanding of the safety issues like high voltage and potential to cause fires and all that kind of stuff. So that's been kind of a real challenge, and specifically around the training, it's getting the right training for the operations team, because the sort of the skill set is so in demand at the moment. Just from the building side, from the design side, that trying to find people with those skills or trying to find the right training for people to do the dismantling is quite challenging as well. But yeah, I mean the time is difficult as well. I mean, if you sort of look into the future, and you say that there are 2 million vehicles being scrapped each year, if they all turn into 2 million batteries, and each one takes, I don't know, an hour to dismantle, that's 2 million hours worth of dismantling that needs to happen in the UK. So it's how do you find that? And then there's the potential trade-off. Do you just try and get to a point where you can shred it as soon as you can? You shred it as soon as you can, at a module level, or even at a pack level if it's not a huge pack but a medium-sized pack. But then the trade-off there is then you have a whole load more materials that you need to separate. So it's that kind of, do you want a harder separation, or do you want less time up front?
Okay, so I guess that the initial challenge, we've got a bit of an idea now of what the challenges are prior to processing. What about processing itself? So I'll come up with this. I mean, I'll give my own thoughts on this first, just from a little thing, and then you can take it from there. But we tried to buy a shredder quite recently, sort of an off-the-shelf solution from a company in Germany, and it was a small shredder, something that could shred only, say, one module at a time. And we got quoted something like £350,000. And this shredder is obviously all singing, all dancing. You've had your sort of fire detection, inert atmosphere, a lot of control. But £350,000 is a huge outlay for something that you can only shred one module at a time.
Yeah.
Which you'd struggle to get a few hundred tons a year out of that.
I think that's a question around because this is all quite new, and you're dealing with materials that people haven't necessarily dealt with before. You're trying to get a bespoke performance from a piece of kit that's off the shelf. So you're starting with a piece of kit that's off the shelf, and then you have to modify it so it gives you the bespoke performance. And part of the problem with that is, again, the volume that, as you say, there are very few people doing it. So there isn't the market there for, the equipment to supply it. So you would have to hope that in a few years, when there are a few more people, looking at it. I mean, it's a conversation that we've had with equipment suppliers. They've said, you're doing battery recycling. What do you want? If you tell us what we want, then maybe we'll be able to come up with something. Okay, it'll work for you, but then for ourselves, we might have something that we can offer to other people as well. But it's making that sort of first step that's the challenge. Yeah, you're absolutely right. It's and it's not just for the shredding; it's all the different separation processes. They're all they've all got their unique features that aren't necessarily that lend themselves to off-the-shelf equipment. Yeah. And
Okay.
then,
So yeah, what about post?
Yeah. I was just gonna. So then you get the material out, and again, it's a question of supply chain. It's where is the supply chain for, for instance, your black mass. So the things that we produce from our process, we've got the black mass, which is sort of the mixture of cathode and graphite. We've got the aluminium and the copper, and we've got the plastic, and then we've got the other metals. It's finding outlets for them. So the cathode, it's got some valuable materials in it, but you need to find an outlet for it, and ideally we want to have an outlet here in the UK, and there are a couple of people who can deal with it, but again, because it's such a new material, it doesn't quite go into their feedstock in quite the same way as their other materials would go. So it's understanding all that. Yeah.
Yeah, when I was working in the industry, I sent some material off for recycling as well, and I found that they only pay for the copper, the nickel, and the cobalt. So any lithium you might have in there, and lithium is I think the second most expensive metal that goes into a battery now, after the nickel, because obviously the nickel is much more in quantity. The cobalt's been reduced, although before it was the cobalt that was the most expensive thing. And the lithium you don't get anything for.
Yeah. So but I mean that's something that you're working on, isn't it?
It is, yeah. So we'll get onto that in a bit. So yeah, you've also got to find the right, I guess, the right customer as well, the one that will pay you the most, but also pay you for the metals that are present in there. So not just waste, lithium, for example. And yeah. So,
well, I think one of the problems there is that you've got these kind of incumbent refiners who specialize in specific areas of materials. So the people who deal with the cobalt and nickel aren't. It's not that they're not necessarily interested in the lithium. It's just that they haven't got the processes to get it out. So it's not of value to them because they can't get a value out of it.
Yeah, and this is, I guess, where we come in.
Yeah.
So so we're working on a number of projects. So one of the things we're looking at is lithium recovery. So what we want to do is we want to get a process where prior to sending the material off to the refiner, you can actually take the lithium out. And one of the ways we're doing that is to try and make the lithium soluble. So you can do that by, for example, high temperature decomposition. So if you get a metal oxide, let's say a lithium cobalt oxide, you put it in a furnace at about 600-700 degrees Celsius. The chemical structure decomposes into lithium oxide, which then you can put in the water and you get lithium hydroxide. Sorry if I'm being a bit technical, guys, but once the lithium hydroxide goes into the water, you can then separate it from everything else. And what we're planning to do is to use a semi-permeable membrane where you can then purify the lithium in one step. But of course, that's one of the projects that we're doing. We're also doing other projects on purifying of the materials. We're trying to increase the throughput through a shredder. We are, but obviously, there's quite a lot of challenges, not just technical challenges, but there's also challenges with regards to recruitment. So, for example, at the moment, it's really difficult to recruit at universities because of Brexit. So, and the visa situation in the UK doesn't help as well. So, for example, if we're trying to recruit somebody from abroad, and we can only offer them a 2-year contract, and if they have to pay £5,000-6,000 for a family of 3 or 4 every 2 years, then it's not very, why won't they go to the US, for example, where they don't have to deal with that nonsense. So yeah, we're a bit hamstrung when it comes to.
We should probably stay on the technology here, really.
We should.
But I think one of the other things that you've just sort of told me about before, and I'm quite interested in is you talked about kind of the lithium recovery, and that's using a furnace at quite high temperatures, and using high temperatures is quite a high cost. But if you can do some processing at sort of room temperature, and I think this is where the things like the solvents, the different solvents that you're using come in. That sounds quite interesting as well.
It does, yeah. So we're developing another project that we're working on is the use of deep eutectic solvents. So one of the, I guess in the future, it's not only going to be the recycling efficiency of a process that's going to set it apart, it's also going to be the carbon footprint as well. So deep eutectic solvents are basically, you get these two chemicals which are solid at room temperature. But once you put them together, they become like an ionic liquid, and then they have the properties of dissolving things. So we're looking at deep eutectic solvents to recover lithium, cobalt, etc. And they're green, so you can use things like choline, you can use urea. And the second thing is they have a low environmental footprint compared to acids. But the great thing about them is that they can be tuned to a specific metal. So for example, if you can have a process where you put it into one and you take the cobalt out, and you put it into the next step where you take the lithium out, etc., then that's the ideal scenario, and hopefully that's what we'll aim to get.
Yeah, no, that's really interesting, and I think that point about greener processing as well is very important. I think something else that sort of taking a step back to what we were talking about before about the discharging and dismantling, that's something that you're doing quite a lot of work on as well. I think one of the problems, like I mentioned, is the time, and not just the discharging, but also testing packs for safety and also for applicability for second life and things that that all takes time. It can take hours, can't it?
Yeah. So I spoke to a company that's developing a process for triaging these battery packs, and they said that it takes a day to triage one battery pack. So you were saying earlier on about taking hours to dismantle a pack. So prior to that, if it's going to take a day just to find out if the pack is good enough for recycling or second life, then it's it doesn't really work there. So what we're doing at WMG is we're developing a rapid triaging technique. So that will reduce the time from a day to 5 minutes. And and so far we've tested it at module level, and it can give an accuracy of about 98%. So our next step is to try it on different types of modules, and then hopefully try it on pack level. Yeah. And if that works, then it's truly a game changer.
And does that grade it then, or does it give it is it like a pass fail thing, or is it could you sort of grade things to A, B, C, D?
No, you can grade it. So it gives you a state of health. So a state of health is, for example, how much of the original capacity is still remains within the pack. And so if you imagine, what we do is we train the tool. So we get a number of cells and modules, and we run them through a number of aging tests. And then once you put a certain, a certain signal through it, it responds differently at different states of health. And so if it's at 80% capacity, for example, if you put that signal through it, it will respond in a certain way. And when it does, then you know that it's at 80% of what it was initially. So I mean, all these things we're doing, but there's in the background, there's also the legislative aspect of it as well. So for example, the European Battery EU Battery Directive, the European Union Battery Directive is currently being updated. I don't know if you know about this, Sam, but you certainly know about this aspect. So at the moment, it's 50% recycling rate. So any recycler that plans to recycle batteries, in particular lithium-ion batteries, they have to ensure that 50% of the material is recycled. And as a caveat to that, what we mean by recycled is 50% of the stuff that you put in, 50% of that has to be a product at the end of it that you have to sell. And so they're currently being, the proposed changes would ensure that it increases to 65% by 2026 and then 75% by 2030. So I guess my question, Sam, is firstly, do you think we can meet these targets? And secondly, given that you used to run a plastics recycling plant, so you've probably got more knowledge than anyone else in non-metallic recovery. Do you think it's possible to recycle 70% of a battery?
Yeah, well, I mean, that's a great question. I mean, there's a couple of things to think of. First of all, the way, just to clarify that 50% thing, that's 50% specifically for other batteries, which includes lithium ion, and then you've got your lead acid and your nickel cadmium, which have their own. I think if you look at, for example, lead acid, I mean, it's a different chemistry, obviously, but they say they can recycle 99% of the battery. So there's certainly something to aim at there. I think the other thing is exactly how you define the recycling efficiency, because if you're looking at it on a cellular level, then that's one thing, but if you're looking at it on a pack level, then that's a completely different it's a completely different challenge, because you've got in a pack, maybe 60% of the pack is the actual cells, and then you've got 40% is everything else, which is plastics, copper bus bars, steel, aluminium, and that's all, there's all incumbent, relatively straightforward processes for that, as long as it isn't anything sort of weird and wonderful. And that's kind of the big question, because you could either have a pack where 40% of it is sort of relatively standard materials that you can, provided you can get them out, and that comes back to your sort of time versus cost versus benefit analysis of dismantling them, then you're already 40% of the way there. The flip side is, if you start designing packs with things like composite materials, then you're losing 40% before you even started, because composite materials are so much more challenging, to the point of impossible to recycle. But then if you get down to the cell level, well, I mean, what we found, you asked about plastics specifically, what we found is the plastics that you recover is actually a very clean stream. That's it's just the plastic, and if you're thinking about the plastic separator in particular, that is quite a nice quality of plastic. As I say, it's quite clean. It's all one material, and I think the problems that you typically have with recycling of plastic film don't apply, because the issues that that are in sort of the wider plastics recycling sector with film is contamination from things like grease and oils from your crisp packets, and the fact that you've got, again, in your crisp packets and things like that, you've got plastic backed onto aluminium, and you've got two different types of plastic backed together that aren't compatible. You don't have those issues with kind of the plastic separator, but it's finding the outlet for it, and that really comes down to volume and things like that. I think the other thing is the 90% cobalt, nickel, copper recovery targets that they're putting in. I think the question is also there. You've got to think about all the steps. If at every step you have 95% recovery, which is a pretty good recovery, you only need a few steps before you get below 90% recovery.
Yeah.
So it's not just a question of how good is the copper refiner or the cobalt refiner, it's how good are all the steps before that as well.
Mm-hmm. Yeah. And obviously, I guess the other question then is, are we able to meet these targets? So, if, for example, by 2030 you have to use 4% lithium in every 4% recycled lithium in every cell, can we meet these targets? So I've had a go at this actually. Just before we started, I thought I'd give it a go to see if we can meet it or not. And so I've assumed that in 2030, we adopt these battery directive. In 2030, we have to, every new cell that we make in the UK, we have to use 4% recycled lithium, for example. So assume that we've got a 50 gigawatt hours worth of cell production capacity in the UK for vehicles. And I worked out that if you take the NMC 811 chemistry, for every 1 gigawatt hour worth of production, I guess we'd need something like 3,333 tons of cells. And so for 50 gigawatts, we need something like 170,000 tons of cells. We know that, for example, each cell has about 2.5% lithium. So by 2030, we'll need something like 170 tons of lithium per year. And, 4% of that is actually not that much. Sorry, no, we need 4,250 tons of lithium, and then 4% of that is 170 tons a year.
Yeah.
Yep. And actually, we can make 170 tons a year by just recycling about 50,000 cars. So every battery, if we take a 250 kilogram battery, it'll have about 3.5 kilograms of lithium in there. And so, if you work from there, for 50,000 cars, you'll get your 170 tons per year of lithium. So actually, we can meet the targets quite easily, I think.
Yeah. So I guess it's the question of what's, it's not just can we do it, but can we get the feedstock to do it? Are there going to be 50,000 vehicles being recycled in 2030 that have those?
I think so.
You would think so, yeah. I think
because you'd also have to look into the so it's not just the cars. You'd also have to look into the gigafactories as well.
Yeah.
So if we take even a small gigafactory that say 20 gigawatt hours, it'll produce something like 80,000 tons of cells a year. And we know that about 10% of those are going to be defective, and you've also got production scrap as well. So all of that taken into account, I think we can meet those targets. Yeah. The only issue is putting the processes in place in order to do it. Because at the moment we're sending a lot of the stuff off to the EU, which is like you mentioned earlier, and we want to ideally have it in the UK.
Yeah, I think the other thing is kind of the traceability of it, because in order to say yes, this cobalt or this lithium or whatever is recycled lithium, there needs to be this kind of sort of traceability of it's come from here, then it's gone into the refining process and it's come out. But there are other things going into the refining processes as well.
Yeah.
It's kind of like that kind of the palm oil certification, where you either have certification that this palm oil is completely sustainable versus this palm oil is a sort of a mixture of things that are probably sustainable. And if I've explained that correctly, but
yeah, I think that's going to be a bit difficult to do, but you can see that a lot of the OEMs, or some of the OEMs, they've taken steps to rectify that. So for example, VW, they've got their own in-house recycling process. So everything they put in there is going to be recycled. Anything that comes out, they know that this is 100% recycled. So they have taken the steps to that. But again, it's something that we'd have to incorporate into the calculations.
Yeah. And I think at the end of it, that all kind of comes down to economics as well, doesn't it?
Yeah.
Yeah. And the value of the materials that are in the cells.
Exactly. So if we look at the different types of chemistries, at the moment everybody's focusing on recycling NMC, so your nickels, your cobalts. Not many people are focusing on LFP, which is the lithium iron phosphate. And actually, there's actually a big move happening at the moment now, which is or a big debate. In 10 years' time, is it going to be LFP that dominates, or is it going to be NMC? And so, if you look at China, for example, they've got this thing called the blade technology for the cells. And what they do is they take these very long sort of prismatic cells, and they cut out all the module bits, etc. And so by the structure of the pack is basically held up by the cells. And because they're using much larger cells, there's a lot less connections that are needed. And so although the LFP cells themselves might have a low sort of energy capacity as compared to NMC, but if you have larger and more of the cells in the pack, so instead of 60% cells, if you can have 80-90% cells in a pack, then you get a higher energy density of the pack, which is comparable to the NMC.
Yeah, and I think as well, you're seeing in China, you're seeing moves towards LFP recycling. There's just seen this morning actually about GH Tech establishing a facility for LFP recycling in the next couple of years. I think 20,000 tons or something like that, and they're suggesting that it's going to be a profitable industry, profitable business. So there is hope there as well.
I guess So I guess from a recycler's perspective, for someone like yourselves, for example, you don't really want to see the shift towards LFP.
Well, I mean, no, it's a kind of it's a seesaw kind of effect, because the people producing the batteries can pay the money to put the cobalt in now, and then the batteries that they produce, the waste batteries, don't cost them so much for recycling, or they might even get a rebate on them, versus taking all the cobalt out, and then having to pay for the recycling in 10 years. But I mean, if you take that argument to its logical conclusion or illogical conclusion, then they should just cover them in gold. Yeah, I mean, it's certainly, it makes the batteries less attractive, but you've got the legislative pressure that says that they have to be recycled, and the producers are financially responsible for them. So one way or another, they'll get done. So I think anything that can sort of reduce the ticket price for electric vehicles and reduce demand on kind of difficult to access materials as critical materials is got to be looked at quite strongly.
Yeah. So you mentioned that sort of there's a legislative pressure, and this comes from the producer responsibility. And so at the moment, obviously, every battery that's recycled, or at least I guess every battery that's recycled, the OEMs are paying a gate fee for it to be recycled. So do you think there'll come a point where it will switch over from a gate fee to where different recyclers are actually competing with each other to buy these packs because they do have a value?
Potentially, I think there's an element of that happening already. Really, I mean, you can go on eBay and you can find Second Life modules from whatever battery pack for sale for replacement in your battery pack. So I think in terms of Second Life, there is an element of that happening already. When it comes to kind of material, I think that's a difficult thing to kind of predict, especially if you are focusing on taking a lot of the valuable materials out. I think in order for that to happen, you'd have to get to not just a material recycling process, but a cathode recycling process. This kind of direct recycling target where you can get the cathode back out and have it as another cathode again. I mean, again, thinking about other industries, there are several other recycling industries where it is driven by gate fees and legislative pressure rather than value, just because that there isn't that value of material in it. So I think if you took it in the round and considered Second Life as well, then yes, potentially you could get in a situation where batteries have a value, but it would only be a proportion of batteries, and recyclers get probably quite good at determining which ones are, especially if they got a 5-minute test, at determining which ones are worth money and which ones aren't.
Yeah, I think it's probably going to be on mileage, if and age as well. So you've got the the sort of the electrochemical degradation that occurs through use, and then you've got the calendar aging. So both of them combined. So if you've got an old battery that's been driven hard, I don't think you need to test that. You just probably think, this has been 150,000 miles. It's 12 years old, 13 years old. Yeah, it's probably not going to be good enough for Second Life. But then conversely, if you've got a 5-year-old battery that hasn't been tested much, you can probably tell actually, it might be good enough.
Straight away, yeah.
So the issue I have with Second Life is that, and coming from somebody that works in battery recycling, of course I'm going to have issues with Second Life. But the issue I have is there's a lot of research that's going into Second Life, which is good. But how much capacity is there for Second Life batteries? So if you've got 2 million vehicles coming to the end of life, that's 38,000 vehicles per week. You've got, and this is in the UK alone. So
where's it going to go?
Yeah, where's it going to go? In the first year you might get 1 million into a Second Life application. In the second year, you might get 1 million. In the third year, but then pretty soon, that industry is going to be saturated. And every Second Life application is not just going to last for 1 year. It's going to last for a further 10, maybe 15 years. And so that's 10, 15 years where they're not going to take anything else.
And I think the other thing is a question of timing, because we're talking about what would Second Life be for? Storage for renewables, for example. Well, those need to be coming on stream now, not in 10 or 15 years. So, you know, you might even get a point where just because of necessity, they get installed now with mostly new batteries, and then there's literally nowhere for them to go until those ones have, you know, have done their life. So yeah, so I think it's definitely a challenge. It's very, very uncertain market, as you said.
I think. Sorry, Sam, go on.
No, you go ahead. You go ahead.
I was going to say, before we go to the questions, I guess the one question I wanted to ask is, who do you think is going to be the one that makes the most money out of this battery recycling?
Gosh, that's a difficult question. Nobody? No. I think it's. You've put me on the spot there, really, but I think there's opportunities for everyone in the supply chain, but I think it's really kind of the battery recyclers where kind of the exciting technology developments are happening, where, you know, new things are coming out and where margins could potentially be improved or cost reduced. So that's kind of where I'd put my, you know, where I'd be watching.
I think it's the vehicle recyclers, actually.
Yeah,
I think they're the best place to get the battery packs, and you know, they can determine whether it goes for second life or whether it goes for recycling, and in either case they'll get the money. And plus, you know, they've got that vehicle as well with a lot more copper than usual, and copper is king in recycling. Yeah. So shall we go to the audience questions, Peter? You're on mute, sorry.
Can you see the one that we've probably got time for one, really. If you go into the chat room, you see it?
Yes, I can see that. I mean, I feel like we kind of touched upon it briefly when we were talking about the work that Anwar's doing at WMG about sort of low temperature solvents and things like that. I mean, I think it's certainly an interesting question, and it's something that makes, you know, when you come to things like composites, it's something that's worth thinking about as well. Is it better to have a recycling process that works but is really high energy intensity and so on and so forth, versus producing a material that that over the lifetime of the product reduces, you know, the energy intensity of that product? So, you know, again, thinking about composites, you might have a much lighter vehicle that over the 10-15 years of the vehicle outweighs the fact that it's much more difficult to recycle.
I'd answer this in a slightly different manner. So recycling is a high energy consumption activity. Well, actually, it's not that high energy consumption. You know, compared to other industries, it's a lot lower. But you know, what's the opposite? You know, getting it from a virgin material. So if we take cobalt, for example, if someone like Sam can get the cobalt at the batteries and gives it to a refiner 100 miles down the road, and you know, they then do their process, you know, get the cobalt back out and, you know, purify it and then put it back into a battery, surely that's a lot less energy consuming than someone from, you know, in the DR Congo getting it out, transporting it to China where it's, you know, refined into something, and then transporting it to Korea where it's put into batteries, etc., etc. So surely, you know, when you compare it to that, recycling is a lot more, a lot less energy consuming and a lot more environmentally friendly.
I would agree with you for a lot of materials, yes, especially for those ones like you've mentioned that, you know, that need heavy industry for the sort of the mining and all that. Yeah. Sure.
So who do you feel should be the owner, if you like, of the battery? Given some of the areas.
Sorry, go on, Peter. Sorry, carry on.
Well, given some of the information that you were giving at the beginning in terms of the sheer volume of sort of processing that will have to be done, given how many million vehicles or hours are going to be taken to do, if the vehicle manufacturer owns the battery throughout the period of the vehicle, then obviously could that ease the flow of recycling towards the end, that they could envisage the peaks of where they're going to need and fill the gaps up? if that makes sense.
I think a lot of it comes down to the fact that, you know, no matter who owns it, it's, you know, possession is 9/10 of the law. Who's got it? If the person who's driving the vehicle has got it, then they can just, you know, just like Anwar was talking about with the vehicle recyclers, they can decide what to do with it. And then when it goes to a recycling facility, they can decide what to do with it, whoever sort of owns it. And if there's opportunity for getting value out of it for second life, then, you know, it's the person who has it who can decide to extract that value, really. So it's how do you enforce that ownership? Would be my question to that.
Yeah, and then there's a lot of other issues with that ownership model as well. So if the battery and the car don't belong to the same person, then, you know, once you're selling the car on, for example, and it just creates a lot of issues. And I think that model has been tried in Europe, but it just doesn't work in Europe. So I'm not sure. I mean, potentially it's a really good idea. Yeah, you know, potentially when the battery comes to the end of life, or vehicle comes to the end of life, all the batteries end up in the same place, and, you know, they can then decide what to do with it. But I think it's probably more expensive for the OEMs that way, simply because it creates problems in the, you know, it creates legal problems when it comes to, you know, for example, say you're selling your car, would you sell it when the battery doesn't belong to you? How much is that car worth, less the battery, etc. So there's a battery ownership, I don't know, it creates a lot of issues. And yeah, I'm not sure if that ownership model would work. Another thing maybe to think about for some other time is, you know, what's happening to the ownership models of vehicles. You know, so nowadays, you know, you've got one vehicle that's shared by, you know, 20 people or whatever. You know, that's probably something else to think about as well.
Which will only be hastened by things like autonomous vehicles as well.
Yeah.
Yeah. Who decides then? The car?
Yeah, exactly. Yeah.
Thank you both. That was really interesting.
Oops. I think Peter's
one
gone.
that's watched, and all the people that will watch on catch up as well. Look after yourselves, and we hope to see you again in the not too distant future.
Cheers, Peter.
Thanks, Peter. Thanks, Anwar.
Thank you.
Thanks, everyone.
Bye.
Bye now.
Bye-bye.
Bye.
Bye.